Thank you so much for the introduction, Lara and Chiara. So, hello everyone. Welcome to this presentation. In this webinar, I will have a short overview on finite element modeling works we carried out over the past few years using FreeFEM in the field of computational biomedical engineering, and also generally on the tool itself. So the outline of the talk will be like, on a couple of headlines. The first one, and is actually the most important one, is the finite element modeling as a general term, because in the field, especially in biomedical engineering and mechanical engineering, these terms usually used for, simulations in solid mechanics. And then I will show you that this is actually a method for solving differential equations. And then I will introduce FreeFEM as a finite element language or tool that we can use to solve partial differential equations. And then I will show you a bunch of examples we had using FreeFEM in the field of biomedical engineering. And I will have also a short overview on high performance computing that is quite easy to do in FreeFEM. So as I said, when we talk about finite element modeling, these are the kind of, usually simulations that people think about. You have a structure, you mesh it, you divide it into elements, and then you perform, you apply some loads, boundary conditions, and then you want to get some, stresses or deformation out of it. And this is actually true. This is still finite element, but it has actually a broader meaning. That was actually, it is when finite element started, but after that, mathematicians saw that, yeah, this is actually a nice idea. We can apply the same principles into like numerical methods, and for that, we can solve equations pretty similar to other numerical approaches. So I would say that finite element is not only for solid mechanics and solid biomechanics, but it is applicable for fluid mechanics, for material science equations, for equations that would derive from mass and heat transfer, and generally speaking, anywhere we have equations to solve, and more specifically, partial differential equations to solve. So in a couple of slides, I will show you some examples of equations and then the corresponding visualization of the results that we solved inside FreeFEM and finite element modeling in general. So this is Navier-Stokes equation with the continuity equation. And when we solve that using finite element modeling, and as I said, this is in FreeFEM, we can have like the evolution of the flow field, as you can see here, that bypasses an obstacle, and then kind of, the patterns that form behind it. The next example is for material science, where we have the corrosion and biodegradation model as a set of differential equations. I will show you more about this, this topic later on. But as you can see, we can have like the diffusion, reaction, convection equations being modeled. And as a result, when we've solved this equation, we can have simulations results like this. This shows the release of material and the surface of the implant degraded. The next example is from tissue engineering and cell viability. We put cells inside some containers, some wells, to provide oxygen, and then we can model the consumption of oxygen, again using a diffusion reaction model. This is another example from, again, tissue engineering for tissue growth models. We see cells on a surrounding of some scaffolds, and then using a phase field equation, we can describe how they grow. This is a curvature-dependent growth, so we have higher growth in regions with higher curvature. I will show you more about this later on. Again, an equation that we solve with finite element, and this is another one using a different technique called level set, where we can really investigate the effects of different geometrical properties of the scaffolds on the rate of tissue growth. Next example is a coupled problem in multiphysics, like diffusion, convection together, depending on the type of diffusion. We have diffusion regime. On the right, we have high diffusion. On the left, low diffusion. This is the partial differential equation. So as you can see, coupled and having like the effect of convection also in the diffusion equation. So this is the result. And so having the same thing also, with a couple of obstacles. This is written for heat. So for temperature, this is more or less the same. So as you can see, the finite element is not just for solid mechanics. And very similar to that, we have elements. So finite elements, that's the terminology. So the domain is divided into elements, and we call them mesh. And then we solve the equations, the partial differential equations, inside these elements. So as you can see, this is what you see is usually the kind of visualization on the left, but behind the scene is actually what is happening on the right. This is another example that when you see the visualization results of the output of finite element, you usually see what is depicted on the left, but at the same time, we have the mesh on the right. And as you can see here, for example, we can have also mesh refinement. I will show you more examples that you refine the mesh, the size of the elements under regions that are more important for you. This is another example for the cell viability that you can see that's the mesh multi-material. We have two regions actually in gray and red, and on the right, it is the visualization. So let me quickly show you that actually what I mean here for applying finite element as a numerical method to partial differential equations. So in the first place, there are a bunch of various methods. And here I want to just discuss finite difference because it is quite known, I would say, commonly used for solving partial differential equations in the field of biomedical engineering or chemical engineering. And finite element, of course, that is the topic of the presentation. But there are really much more methods with their own advantages and drawbacks. An example that I want to show you is a reaction diffusion PDE that we have like U as a function of X and T. Now, I don't want to go into the mathematics a lot in this presentation. These are a couple of slides just for the reference that you can also, as Chiara said, you can watch the recordings later and go through these slides more if you are interested. So then we have like a diffusion reaction PDE describing the way that U is diffused and then how it reacts with the surroundings. So just model simply using this term here. And then I want to see, how I can solve it. And as an example, the equation that I showed you for the biodegradation and corrosion is very similar to this. So as you compare these two things, you can see that actually I have omitted this term, which is just a constant. And then this is the reaction term, and this is the diffusion. So if we want to solve this using finite difference, I think many of you already know this, that we can divide this space, this is called discretization, into a number of elements. In this case, it's one-dimensional, so we have just X and T. And then we discretize the temporal term like this, and then the right-hand side can be discretized according to the adjacent nodes. And with this kind of notation for matrix notation, we can also divide the diffusion like a spatial dependent diffusion term and a reaction like this. And this is very, very easy to implement inside any program. This is 1D, but it can be extended to 2D or 3D. So the main advantage here is easy implementation. But the main drawback is that, with finite difference, it can be quite difficult to deal with complex geometries. And this is where actually finite element can show quite some advantage, I would say. So in finite element terminology, this is really important because this is what FreeFEM deals with. And in order to use tools like FreeFEM or Phoenix that we already had a webinar on that, you really need to learn this, the mathematical background that is also very easy to get. So in this case, we call the equation, the partial differential equation we want to solve, the strong form. And then we apply, a mathematical technical variation of formulation and final space on that. And then we get a weak form, a form that looks like this. I will quickly show you how it is derived. And this is a term that you need to, work with inside tools like FreeFEM. So the only prerequisite that you need to know to work with tools like FreeFEM is learning how to go from the strong form to the weak form. The way that we do it, I go back again to the equation that I showed you. Here is the reaction diffusion equation, and we divide each term of that by an arbitrary function v. V has some properties. I don't want to go to the details, but I just want to show you how simple it is. And then we apply, we integrate all the terms according on the whole mesh that we have, like on the entire mesh, computational mesh. And then we divide the terms. The second term can be divided, integral by parts. And then here we can apply boundary conditions. This is the boundary of the node, boundary of the domain, sorry. And in a lot of cases, it can be eliminated based on some, properties of u and v. And in the end, we get something like this. And actually, the temporal term is also discretized using finite difference. So in the end, the weak form is a combination of finite element and finite difference. So this is really like the way that you can derive the weak form. And then the next step is to get this, the weak form, into a form that like AU equals B or AX equals B, linear system of equations. And this is actually what FreeFEM does for us. So FreeFEM can integrate the weak form that I showed you on the entire domain. So it means that you just need to derive the mathematical equation, convert it to weak form, and then FreeFEM can convert it like this kind of weak formulation into a code, and then solve that on any shape, on any geometry, on any mesh for us. So this is really like the essential concept to grab, that this is a little bit different from other tools like COMSOL, ANSYS, or Abacus, where you apply like boundary conditions on geometry, and you usually do not care about models behind the scene. Here is the advantage, that you can deal with any type of equation. It's a lot of cases you derive yourself from the biology or chemistry or physics behind the scene, and then you can solve it on any mesh, let's say. So as you compare the weak formulation, the way that it is implemented inside FreeFEM, you can see that it's very, very similar to the mathematical notation. This is also the same for Phoenix or other tools that work on the same principle. So, from the tool, then from the same techniques and the methodology and the tool, we took advantage a lot in the Biomechanics Research Unit at the University of Liège and KU Leuven, under the supervision of Professor Lisbeth Giris. We developed a wide range of different models from tissue engineering and bone tissue engineering, biomechanics, and also a little bit of chemical engineering using this. And the reason that FreeFEM was quite beneficial for us for the things that I will show you from these slides on, the fact is it has some certain advantages. The first one is FreeFEM gives us a lot of freedom in controlling finite element spaces, and that is something that is very crucial and is usually limiting when you work with tools like COMSOL or Abacus. And it allows us also to go for like a high resolution or having control on the implementation of mathematical models that we want to have. And as an open source tool, and it's almost the same for all the other open source tools, that they use open standards and exchange formats. And as a result, you can easily create some orchestration of tools, mostly open source tools, working together to produce the result that you want. So interoperability is actually is in a high level using open source tools. And then FreeFEM has a nice integration with some other scientific computing tools like PETSI. I will talk about this, and some really high performance domain decompositions and mesh generators and really high class solvers. So all these three things will give us a high degree of freedom and also a flexibility to deal with any kind of computational modeling projects. So let me give you a couple of examples about the different models that we implemented using FreeFEM. The first one is about a biodegradation process. That was actually my PhD. So we say that this kind of implants, when they are made from biodegradable materials, they can dissolve upon fulfilling the mission inside the body. They can disappear, and no further like surgery is required to remove them. And the thing is, the biodegradation behavior can be should be optimized based on different types of applications, whether it's cardiovascular or orthopedics. And the process itself can be described by a set of reaction, diffusion, advection differential equations. So very similar to the equations that I showed you. So I think you can see where we want to go. So we can derive these equations from the chemistry, underlying chemistry, and then we can use FreeFEM and finite element to solve them. Really as easy as that. And for this one, because we also want to track where the geometry, how the geometry and the surface of these implants evolve over time, we can also employ moving interface tracking method like level set of phase field that just adds another PD to solve. So that's the only thing that matters here. So another PD that we solve again using finite elements. This is, you already saw this. So this is the type of results that we have. As you can see, the release of material in the medium, and then the blue surface depicted on the right shows the level set function that evolves. And this is really like a model comprising of around 6-7 partial differential equations describing how the concentration of components change over time in different nodes of the computational element of the computational domain, and then the visualization would be like this. This is another example for a porous scaffold. As you can see, we were also able to model the side corrosion products on the surface of these implants, depicted on the left. And then these are the models that we use for validating, for validation and verification. You can see again a very narrow cuboid degrading and releasing material to the surrounding. And then on top of that, we developed a model. So it's quite straightforward to link the underlying FreeFEM codes and models with some high-level software tools like C++ and Qt. And in this case, that's what we did. The feature is a cross-platform interface that can control the FreeFEM backend. Kind of, we can look at it as a front and backend program. It includes also pre-processing and post-processing for sure. So we say that it has a FreeFEM backend and C++ front end, and then we had like a full feature program. So this kind of communications is also quite straightforward and possible. And this tool is available as an open source software on GitHub. And using the same models, these are all implemented in FreeFEM. We coupled this biodegradation model with some topology optimization models, still again implemented in FreeFEM, in order to see the effect of biodegradation on the shape that we want to optimize. So what you saw there is actually like a problem like this, that we have two holes inside the material block. One is fixed, one has an applied load. And then depending on the kind of constraint that we have, we can have this kind of, the evolution in the shape that gives us the most optimized shape that we desire. And later on, I will describe these kind of things that we see here. As you can see, we have some very small element, like boundaries there, super like narrow white region, and those are for parallelization. So I will describe it later on. And these are the simulation results. As you can see, the degradation, releasing material inside these infield objects. The next project I want to show you is a computational modeling of tissue regeneration. So the one that I showed you, that we seed cells on a surface of the scaffolds and then they grow. So we want to model cell growth on porous, open porous scaffold. And the goal is to investigate the effect of pore size, shape, curvature, and these kind of things that we characterize as geometrical characteristics. And for that, we had a computational model of the tissue regeneration process that is curvature-driven tissue growth, actually. And we had two sets of different models using level set and phase field. So these are just different differential equations that try to correlate the curvature to the growth of the new tissue, let's say. So this is the stimulation output inside a bioreactor. The effect of the fluid flow is considered as well. So an extra term in the PDE, FreeFEM doesn't care about that. So if you have it inside the mathematical model and you derive the weak form, it's already there inside the model. As you can see here, we can also investigate the effect of the geometry on the rate of the tissue growth on the different type of scaffolds. And as I say, I will discuss parallel implementation later, but this is the way that we decompose the mesh as depicted on the left into different subpartitions, and then we have, as a result, we will have faster simulations. So as you can see, it grows faster in regions with higher curvature. The next project is computational modeling of pancreatic cell viability. So that is for addressing some issues that we have in islet transplantation to treat diabetes. And this kind of transplantation, when they are grouped into, like the cells are grouped into islets, they are really vulnerable because of lack of oxygen and like supply of oxygen. And as a result, they are usually put inside some devices that you provide oxygen from the surrounding, from the boundaries of the well, using a gradient-driven oxygen supply, let's say. And then we wanted to model this using a set of, actually it was a single reaction diffusion equation to assess, to investigate if the cells can survive or not, or they will die, depending on different type of conditions that we can have. So in this case, the cells, the group of cells, the islet are in the center, that they start to consume oxygen. What you see here is the concentration of oxygen normalized. And then on the surrounding of this well, of this curved geometry, we will have oxygen being supplied. So then we had like different setups also for optimizing the number of islets that we can have, their size, the size of the islet, and also when we put them all together, this model allowed us to investigate the optimal kind of setup that we can have for the well and a device that provides oxygen. So the equation that describes this, I showed you in the beginning when I wanted to show you the diffusion reaction equation for cell viability and consumption of oxygen. And then the next project is related to computational modeling of bone fracture healing. That is actually the PhD project of Laura, the chair of the session, in which we have like bone fracture healing in different, we want to investigate that in different stages. And this process can be nicely described, the biology behind can be nicely described by the set of, in this case, they are called Taxis diffusion reaction equations. So very similar to diffusion reaction convection. For the way that the cells, biochemical factors, and general tissues, new tissues interact with each other. So again, we have set of PDEs that can be also coupled with a cellular automata model. So these kind of things are also possible to implement in FreeFEM that can be coupled, let's say. So this is what she has done inside FreeFEM. So this is really like a type of output that we can have here, like for different biochemical factors, as I said, cells or the growth of the bone and the bone remodeled, depending on different geometries, different like in vivo setups that the experimentalists in our group have. So as you can see, we have also the vascularization model inside FreeFEM, using a cellular automata. And this is actually visualization shows that, as I said, is kind of really like narrow white lines. They are for domain decomposition. And here it shows that the vascularization can also go from one domain to the other one. This is quite important because each subpartition runs inside one CPU core, and as a result, it's really essential to have some communication here. Now, I will elaborate on that shortly. So, yeah, the next topic that was actually one of the headlines is high-performance computing. And by that, I mean that we want to parallelize the simulations. We want to run simulations using parallel machines on multi-core systems, or we want to have like, you know, run the simulations on supercomputers. So there are a bunch of techniques that we can use inside FreeFEM and generally like scientific computing to parallelize simulations. And one of them is distributing the mesh into like available resources. And that is a technique called mesh decomposition. And for that, as I said, there are some available techniques in FreeFEM. One of them is called overlapping Schwartz method. And as you can see in the figure, it is like we have a mesh and then we decompose it into subpartitions. And then we assign each subpartition to one CPU core or CPU node, or you know, generally speaking, it's one node. So this is the way that we can divide the problem into smaller pieces and run it faster. And all the examples that you saw in the previous slides, that we had like the mesh being decomposed, it was actually this technique. And then another thing that is very important in this kind of high-performance computing techniques is solving the linear equations that is derived. You know, I showed you before that FreeFEM can perform the numerical integration in order to get this linear system. And then after having this, we can have different techniques to run the system faster on a parallel machine. One of the techniques is called preconditioning the system, in which we multiply a matrix into both sides of the equations. It's called the preconditioner. Depending on the type of physics that we want to model, this preconditioner can be different. And then another thing is like, depending on the type of preconditioner we use, we can use also a type of solver that can be direct or iterative. You know, these are really like, there are a lot of details here that are easily accessible online in documentations or also in the FreeFEM documentation. And the thing is, the nice aspect of FreeFEM is that it has a very like nice integration with PETSI, which is a framework for doing high performance scientific computing for a wide range of different applications. And you know, this is another advantage of FreeFEM, that you can easily work with PETSI and learn PETSI, while you know, dealing with PETSI directly can be a little bit more difficult. And then what is really essential is like when you apply this kind of techniques, you need to benchmark if the parallelization is efficient or not. If it is really working when you increase the number of CPU cores and apply and you provide more computational resources. There are different also methodologies and techniques here to benchmark the parallelization. One is called weak scaling, in which we double the problem size and double the resources. So as you can see here, when we double both, we assume we expect to have like the same amount of time, same amount of execution time that the simulation takes to run. So this is a visualization of that. Imagine that we have a problem size depicted on top. It is for multi-material domains. So the blue and red are just two different materials. And then we go for two cores in a simulation. Then we multiply or double the problem size and we double the resources. On the bottom, we have the number of subdomains. So with 2 cores, 2 subdomains, and then 4 cores, 4 subdomains. Again, we double the problem size, and 8 with even double. So in this case, these are not the numbers we usually deal with, but this is the concept. And then there is another one that's called strong scaling, that we keep the problem size constant and we just double the resources. So we expect that when we provide more resources, and for example, we double the resources, we can have reduction, great reduction in the computational time. So this is really like the type of output of this strong and weak scaling. As you can see on the right, that's actually an ideal case that we have a constant wall time. And wall time is a terminology that we use, for example, for a number of seconds that it takes for one time step to solve. So as you can see, in this case, it's more or less something around 28 seconds. As we double the double the problem size or increase the problem size proportionally to the number of cores. And then the strong scaling on the left, you can see we increase the number of cores, and then we have a drop in the wall time. In this case, that's not an ideal case, but this is more or less like the behavior. So if I want to show you one case study that uses this kind of techniques, is again back to the biodegradation simulation for a patient-specific case. And here we have like the hip implant, the cup of the hip implant that is infilled with a triply periodic minimal surfaces lattice structure. And we want to have actually that part to be degradable. So that what you see here on the right is actually the output of topology optimization like model that we have the desired stiffness, and then it is mapped to some volume fraction and a volume fraction to TPMS structure. So in reality, this is not a part that is degradable, but here for simplicity, for like simplification of the geometry, we assume that this is the part that is degradable. So as you can see that the model has a lot of geometrical detail, and this doesn't have necessarily symmetry. So we cannot say that we just investigate only portion of that. So we embed, in order to perform the degradation, we embed this cup inside a container. And there we refine a mesh on the surface. And these are all the things that we perform inside FreeFEM. So FreeFEM has these features, as I said, nice integration with some meshing tools and mesh refinement, mesh partitioning, all these geometry pre-processing tools. We were able to do these things also inside FreeFEM. So we embedded inside a mesh, and as a result, the mesh contains around 45 million elements. So this is a visualization of the mesh, why such a mesh contains this number of elements. You can see the mesh is refined on the interface, and then as a result, we have the geometry embedded inside the container. So this is the computational mesh, and as I said, we have derived a set of differential equations, and we want to solve them on this domain. So the next step is like mesh decomposition using HPDDM library and also PETSI. In this case, what you see here is the mesh being decomposed and distributed to around 2,000 CPU cores. The way that we did it was also, even more for having more valid, strong scaling kind of benchmark. And then this is the visualization using 128 CPU cores that shows how the structure degrades inside the container. And then depending on the different conditions, we can have like a different geometry or different diffusion, different corrosion regimes, or different environments, and all these things applied to this simulation. This is another visualization on top of that. So you can see from a different angle how it degrades. So these are, the type of strong scaling test that can be also decomposed, can be divided into different, let's say, equations. So as I said, we have like 5 to 7 equations, and then we can measure the wall time for each equation, and in the end, cumulatively, as can be seen on the right, bottom right. So this is really like the type of modeling work when it comes to high performance computing. This is what you need to do. You actually decompose the mesh, you solve the equations in different subpartitions, you assemble them, and at the same time, you also benchmark the simulations. So at the end of the presentation, I'll also say, as although Kiara mentioned that in the beginning of the presentation, that in order to find more information on FreeFEM, there is a project I initiated called TalksWriters that talks about these methodologies, both from the mathematical and also the computational sides, in a simplified language. So that was actually the goal, to represent these things in a way that it can reach a broader group of users. And part of it is also demonstrating the power of open source when it comes to scientific computing, as I mentioned, for open standards and the high flexibility that it provides. So you can check it out if you're interested in these topics and you want to also learn the mathematical concepts that you need to work with these tools. And most of the modeling works here are based on FreeFEM. So FreeFEM has a very important role in this, in the content here. But in addition to, talking about FreeFEM in different projects and different models, there is also a dedicated playlist there on FreeFEM that is related to FreeFEM from the very basics, so the language syntax, to up to parallelization and high performance computing, and also PET-C stuff and solvers. So this is actually a playlist that you can check out. As I said, I didn't go to the details of these, the implementation and models generally, but you can refer to this content if you want to learn more about these things. So yeah, thank you so much for your attention. This was the introduction that I wanted to have to FreeFEM. I hope you find it useful and interesting.